In today's video, we're going to continue looking at how we can quantitatively model some of the forces we've been talking about. In the last video, we looked at the different types of friction we're going to be discussing in this class. Video before that, we looked at gravity. Today, we're going to have a quick discussion and look at drag and air resistance. So what is drag and air resistance? Well, you're probably familiar with this. Drag is a force that you're going to encounter anytime you have an object moving through some fluid. So if you're moving through air or water or oil, molasses, whatever, when you move through that fluid, that medium, the object has to sort of push that medium out of the way. So if you've ever stuck your hand out of the window of a moving car or something, or been on a roller coaster, you can feel that your hand or your body is hitting the air, the stationary air that you're traveling through. And when you hit that air, it pushes you back. So it's actually a contact force with the fluid you're moving in. Now, it can actually get really complicated with aerodynamics and the directions of the force and that. But for most objects moving at reasonable speeds through air, this drag force is usually pretty small unless you're going very fast or you're very large. So typically, and especially for this course, we're going to ignore drag and air resistance in our problems. It's typically just too small of a force to have a significant effect on the motion or on what we're looking at. This is similar to how when we discussed gravity and we had the force of gravity exists between any two objects with mass, we ignored most of them because that force was so small, other than when the Earth is involved or some really massive planet. Same thing with air resistance and drag. Unless we explicitly state we're going to be, considering it, it's safe to just ignore air resistance and drag in the problems we're discussing. That being said, there are situations where we are very concerned with this. If you have something like a feather falling where the force of gravity is really small and it's got a large cross-sectional area, those forces might be comparable and drag would be of interest to us. We would have to consider that to accurately model our system. And in the second project of your labs, the actual entire lab is sort of focused on drag. So what we're going to discuss today is how can we model this? There are several ways to model this, depending on, and some are better applied to different situations than that. But again, for most of the situations we're going to see in everyday situations, say a thrown baseball or similar type things where they're moving at reasonable speeds, they're not spinning and rotating and doing crazy things that might cause them to curve in that. A safe way to model it is with this sort of quadratic dependence, is what we'll call it. But we can model the force due to drag as that. And it's always going to be in this model in the direction opposite to the motion. So if you're moving forward through the fluid, you're pushing that fluid out of the way. That fluid's pushing backwards on you, and that force that's exerted from that is going to be opposite the direction of the velocity, opposite the direction you're moving. And what goes into determining what the magnitude is a lot of things. This is essentially the equation we're going to use as our model for drag, and we have a lot of terms in here. A is the cross-sectional area of the object we're describing. Rho is just the density of the air. And both of these things, you can think sort of intuitively of why they matter with this force. Remember, this force is coming from the body or the object pushing the fluid you're moving through out of the way. Well, if you have a larger area that you're pushing through that fluid, you're going to run into more molecules of that fluid. You're going to have to push more of them out of the way. You're going to have a larger force pushing back on you. So that area is important. And if the fluid's really thick or dense, and there's going to be more molecules for you to push out of the way. So it's also going to depend on that. Typically, the density of air that we would use is 1.2 kilograms per meter cubed. That's also given in the text. But both of those things are going to affect the magnitude of the force due to drag. The other thing is this constant c here. This is just a dimensionless quantity. And the way I like to think of it is you know, different shapes have different aerodynamic properties, right? You can imagine a square with a given cross-sectional area versus, say, like a pointed cone with the same cross-sectional area, but the cone is sort of just deflecting the air as it pushes through, not bluntly hitting into it. So they're going to have sort of different um, coefficients or different drag forces, and this coefficient, this drag coefficient, is the way we sort of shovel in all those aerodynamic properties. You know, is it going to, you know, cut through smoothly through the fluid, or is it going to sort of catch a lot of fluid as it goes? The textbook gives some rough estimates for certain types of shapes. If you have a sphere, we can see what some of the things are. So the sphere, if you think of the cross-sectional area, you're essentially taking the widest part of that object, and we have, you know, that area of that widest part is the area in that equation, right? What's the maximum sort of amount of area that you're going to have to push through that fluid? And then the C, which is what's given in this diagram, depends on the shape of it. So if we had a sphere, we're going to have, you know, a coefficient of a drag coefficient of about 0.5, whereas if it was, say, a cylinder, even though the area is the same, you know, this is flat, it's going to be sort of bumping into more air, it would have 0.8. If you had a cylinder moving through its side, it's got a larger area. In this case, it looks like a larger area, and it would have a different drag coefficient as well. So the drag coefficient is one of the big, you know, to calculate those from first principles, and that would be extremely hard and beyond the scope of this course. Typically, we pick a shape that from the textbook that's similar to what we would try to model and start with that, and then, you know, perhaps use our measurements or experimental data to kind of say, okay, this would mean in this model we would have this coefficient of this drag coefficient, and determine that from experiment. So what? How can we use this? All right, one way we can think about this drag is, let's just imagine something falling, right? So let's take you drop something from the top of a skyscraper or something. Let's say we drop a ball. So we have our ball falling down, and if we're looking at forces, so we want to sort of consider the forces, right? So we definitely have that long range force of gravity, and if we're concerned with drag as well, we're going to have drag in the opposite direction of that motion. Now, when we drop that ball, it's going to slowly start to speed up, right? You know, when we first let it go and it's not moving, we have gravity pointing down, and there's no drag force. Velocity is 0, and then as it speeds up, that drag force is going to get bigger, and then it speeds up and gets bigger and bigger and bigger, and eventually, as that object speeds up, that air resistance or that drag is going to get larger and larger and larger. So eventually, what's going to happen is this drag force is going to grow and grow and grow, and then it's going to get to the same size as the force due to gravity. So during this whole thing, we know we have Newton's second law. F net is equal to mass times acceleration. And in the y direction, the direction where we have all our forces, this means we have drag going up, and then minus the force due to gravity, which we learned is equal to m times g. This is going to be equal to mass times acceleration. And at first, this drag term is really small because this velocity in our model is really small. So there's hardly any air resistance, and we're accelerating close to this, well, initially at the speed, the acceleration due to gravity, but then as we start moving slightly slower and slower, eventually this drag term is going to get large enough that drag is going to be the same size as the force due to gravity, and this is going to come to 0. And in that case, this is what we call terminal velocity, right? There's a certain speed, a maximum speed you're going to be able to reach when you're falling under the force due to gravity through a fluid, and that's going to be called terminal velocity. And it's determined by, you know, when the acceleration is 0, when you've reached that constant velocity. And if that's the case, we have drag, you know, we can just bring the gravity to the other side, is equal to mass times gravity. And for the model we've used here, we can just substitute how we calculate that force due to drag, right? But this velocity, this speed that we're moving at is what we call the terminal speed in this situation. So we can actually solve for what that terminal speed would be. It would be the 2 comes up, so 2 times mg divided by that drag coefficient, the density times a, and then we have to take the square root because that speed was squared. And this equation, this tells us what the terminal velocity or the terminal speed of that object falling would be. So we can calculate this a priori, kind of make a prediction for what it is. And then this is what's going on in your lab. You can simulate it, you can calculate it, and predict what that terminal velocity is, and then conduct an experiment and watch that motion and measure that velocity and see if you came close to it or see if your prediction agrees with it. Now, again, this coefficient, this drag coefficient here, typically we're just going to guess for some similar shape to it and get it. So there may be some disagreement here. Another thing you can do is experimentally determine what that terminal velocity is and use it to calculate or use it to determine an experimentally determined coefficient. By essentially, let's assume our model is accurate, and you can strengthen that argument if you want, and then experimentally say, okay, if that model's accurate, we measured a terminal speed of this. That would mean our coefficient, our drag coefficient is this because we know the values of everything else in that equation. But anyway, that's sort of the gist of drag. It's a contact force with the fluid that an object's moving through. We're going to model it as that force always being in the direction opposite the velocity, and with a magnitude determined by this equation right here. With that, you can determine what the terminal speed is. Basically, the maximum speed you're going to get if that object's falling under the influence of gravity in that fluid. Eventually, it'll speed up enough that that drag force will cancel or equal the force due to gravity. The object will stop accelerating because there'll be no net force. That speed is what we call the terminal speed. All right. Hopefully that helps and will help you with your labs and how to think about it and work on the stuff. If you have any questions on the material we're covering, as usual, email me and I will see you in our synchronous sessions.